Warm greetings and good afternoon, dear my friends and students. Today we are going to see about the video lecture on the bending stresses and the shear stresses on a beam, which is of a cantilever or simply supported beam carrying a point load or UDL or the combination of point load and UDL. So you know that due to the loading on the beam, what will happen? The beam is going to bend in the direction of the load. If you are applying a downward load, the beam will bend in the direction of the downward direction. So due to that, what will happen? Whether the cross section of the beam is rectangular, square, or hollow, rectangular, or a circular section. So due to the bending, if it is simply supported beam, you know the neutral axis, that is the centroidal axis, the neutral axis. Above the neutral axis, you will get the compressive stress, and below the neutral axis, you will get the tensile stress. But in the case of cantilever beam, if you are loading the beam, either combination of point load or the UDL, the beam will bend in the downward direction, but above the neutral axis, you will get the tensile stress, and below the neutral axis, you will get the compressive stress. So due to that, what will happen, and what about the reinforcement we have to provide in the case of the reinforcement concrete structural element of a beam, or in the case of a column? So what will be the number of steel reinforcement we have to provide? So here I am taking a simply supported beam with a central point load of 50 kilonewton acting downward exactly at the center, and the beam is of 4 meter span. So you know that the reaction at the support end and the load is symmetrical, so it is equally shared. The shared value of the reaction at A and B, that is at the support ends, are 50 by 2, that is 25 kilonewton, and for the reaction VA and VB, both are acting upward. So here, if you are drawing the shear force, so from A to the point load, that is I call it as support A is A and right support is B, and middle load point or the span is called as C. So for the span AC, you will get a constant shear force of upward, that is plus 25 kilonewton from A to C, the midpoint of the load. Then from B to C, from C to B or B to C, again to change the sign from positive to negative, which is of 25 kilonewton minus because of a negative shear force, and it's constant from C to B, that is at the support B. So here the maximum shear force is of 25 kilonewton, which is from A to B. Either it's a positive shear force or negative shear force, the magnitude is 25 kilonewton. So how to find the maximum shear stress? The given beam is a rectangular beam, which is of 300 mm by 500 mm depth. So in that case, if you are able to find the bending moment, right? So the maximum bending moment is, right, 25 into 2, that is 50 kilonewton meter. So the moment unit is kilonewton meter, which is of magnitude 50. So, and maximum shear force is 25 kilonewton. It occurs from one end to the other end. It is always constant, but only thing is change the sign at the middle point or the under the load of plus 25 to minus 25 kilonewton. So what will happen for the maximum shear stress? So maximum shear stress is equal to Q max or tau max, that is equal to 3 by 2 into Q average. So what is Q average? Q average is the average shear stress, which is equal to the maximum shear force here, F divided by the cross section of the B into D. So it is F divided by BD. So here it is, the shear force is 25 kilonewton. Convert into Newton, you will get 25 into 1000 divided by 300 into 500. So you will get some point of, say, example, 1.432 Newton per square millimeter. So the maximum shear stress is 1.42 Newton per square millimeter. So the average shear stress we have calculated. Then we have to find the maximum shear stress. So Q max is equal to 3 by 2 Q average. Q average is 1.42 Newton per square meter. So multiply by 1.5 into 1.42. So you will around 1.96 kilonewton, sorry, Newton per square millimeter. So that is the procedure to find the maximum shear stress at the midspan of the beam. Or if you are asked the maximum shear stress at any point, you take the corresponding shear force at that point, you get that for a value of the corresponding area. You will get this shear stress at the corresponding section of the beam. Now we are going to find the shear bending stress. So maximum bending stress I have asked. So maximum bending stress will occur at the midpoint, which is of positive 50 kilonewton meter. So M max is equal to 50 kilonewton meter. If you are converting it to Newton to millimeter, 50 into 10 power 6 Newton millimeter. So here we have to use the pure bending equation. Already we know that pure bending equation is nothing but m by I is equal to sigma by y is equal to E by R. So already defined what are the expansion for m, moment of resistance or maximum bending moment, I is the moment of inertia about the neutral axis, and y is the fiber distance from the neutral axis at the center of the beam, either to the top or to the bottom. And E capital E is the Young's modulus of the material of the beam, R is the radius of curvature of the beam, and sigma is the bending stress at the required point. So that I call it as Newton per square millimeter is the unit for bending stress, and Y is the fiber distance from the neutral axis. If you take the top and bottom fiber, which is of rectangular section 300 mm by 500 mm means, so here Y maximum is equal to 500 by 2, that is equal to 250 millimeter, the top fiber and the bottom fiber. So you substitute the corresponding values in the equation. M by I is equal to sigma max by Y max. So if you are putting sigma max is equal to M by I into Y max. M is 50 into 10 power 6 divided by I is 300 into 500 cube by 12 into the numerator. Y max is nothing but it is 250 mm. If you are finding that value, right, you are simplifying using the calculation, you will get the maximum bending stress at midpoint at the outermost fiber of the rectangular section of the beam. So if it is a rectangular section, that is top and bottom fiber. So you are getting say nearly around 2.78 Newton per square millimeter. So the maximum, in the case of simply supported beam, maximum bending stress occur at the top fiber, which is of a compressive nature of 1.78 Newton per square millimeter, and below the neutral axis the maximum uh, that is bending stress, which is of a tensile in nature, will be of 1.78 Newton per square millimeter. So at the neutral axis, what will happen? That the center means at the neutral axis or at the centroid, the bending stress is zero. So because the maximum bending moment will occur at the midpoint, but the bending stress maximum at the outermost fiber, top and bottom fiber, bending stress is zero at the neutral axis. The bending stress will be zero always neutral axis whenever it is a rectangular, square, circular, or any irregular shape section of the beam. So this is about the video lecture on the bending stress and shear stress. I have taken example of simply supported beam with a central point load of 50 kilonewton. Thank you very much for patient listening. God bless. Thank you.